Welcome to EDU World Space.
Here, our goal is to transform the total angular momentum of a two-particle system to the center of mass coordinates. So a reminder that the total angular momentum can be written as a sum of the two individual momenta crossed into their positions. Okay, and if you had three particles, you could add in the third particle as well. But here we're just looking at two particles. The center of mass is assumed not to be moving and in the origin, which makes the two positions on opposite sides of that red X such that their separation can be written as R2 minus R1. Gives us their mutual separation vector. Now you can use the center of mass calculation with the origin equaling the center of mass, and then you will find that the two position vectors remain on opposite sides of that with a fixed proportion. And we won't go through these. These are fairly straightforward calculations. And a reminder that the reduced mass is the product of M1 and M2 over the sum. So a reminder, if, for example, M2 is much, much bigger than M1, basically R2 shrinks to that red X, and your reduced mass is basically going to be M1, and it will look like M1's doing all the moving. So this is similar to planets going around the sun or small satellites going around the Earth. So what we want to do for L total, a reminder that the momentum is just mass times velocity, which I'll write as a time derivative of positions. And so we can take the time derivative of our two position equations and use those to substitute. Okay, so we have time derivatives of both R1 and R2, and we can rewrite our total angular momentum as R1 crossed M1 times mu minus mu R dot over M1. So M1 will cancel, and a very similar expression for the second term. Okay, so yeah, what's nice is the M1 and the M2s cancel. And so our total angular momentum is equal to R1 crossed, and I'll put the negative sign in front, minus mu R dot plus a positive R2 crossed mu R dot. And as long as I don't rearrange the order of the cross product, what this basically gives me, if I add up the two front vectors, R2 minus R1 crossed mu, and we'll call that V. So at the start of this, we said that the difference between the two individual position vectors just gives the mutual separation r. And we can then call mu times v dot the momentum about the center of mass. So yes, we have basically shown that the total angular momentum can be reduced to a very simple expression that looks just like one particle moving about the center of mass. So that's a very nice simplification.